So in question number 7, we're actually going to compare two means. So you'll be using weight and if someone smoked marijuana. Now, once again, I will not be doing the same exact thing you'll be doing, so make sure you do your question and not do directly what I do, but you can follow the same process to get the output you need. We need to make stacked histograms. So let's see here. I'm going to go to my subset of 90. Once again, I'm in the subset of 90. Nothing's excluded or hidden. So let's say I compare the weights of males and females. Is there a difference between males and females and their weights? I want to make stacked histograms right here. So let's go to Analyze Distribution. So we are going to put sex right here in bisex. And then we're going to put weight into the columns. So we're analyzing weight by sex. We get two histograms right here, and we're going to go to the red arrow and click stack. Now we have both histograms given right here, but we do not have them with a uniform scale. At this point, it looks like males weigh more, even though they do. But we don't see the same scaling. Females have someone who weighs a little bit less, and they have a lesser range than males have, or they don't have as high of a maximum. So with this in mind, let's go right here to the top and click uniform scaling on both of these. You need to click it on both, and now they both have the same scale. You can see down, this goes to something a little less than 100, and this goes to 300, same down here. Now I'm going to click the red arrow, and a quick trick is I'm going to hold control before clicking it, hold control, now click it, histogram options, and go to count axis. This actually puts it in on both of them. I think you can hold either control or command on a Mac and it'll do it, but you could have just gone down here also and clicked histogram options, but it's neat, especially if you're doing a whole bunch of stuff. It's easy to put stuff on tons of things by just holding control, and it does it on everything. Need a little quick trick and jump. So we have our stacked histograms right here. Everything looks to be nice and neat. Let's take a little picture of this. And there we go. Going back to what we have right here, make stacked histograms. The bin widths should be identical, and they should have count axis, and we have that. The bin widths are identical, the range down here at the bottom is identical, and we can see that the males definitely weigh more than females. Comment on the difference in similarities between shape, center, spread of these two histograms. What is shape? Shape would be unimodal and symmetric. And there's some skew to it. You could say right skew. They have some small right skew. But that's what shape is. Center would be more, since we're saying they have a little bit of a skew, we probably want to use the median. The median for males is much higher than the median for females. So males on average, the average male weighs more than the average female, kind of obvious there. And spread, males also have a larger spread in the data set, as denoted by, actually, let's see here, yep, the female spread for the IQR is about 25, it's 24.5, I'm doing Q1 to Q3, and the male spread is about, it's about, what is that going to be, is that 45? I think that's 45 right there. Oh no, it's 35, isn't it? Yes, it would be 35. So the females are close to 24.5 and the males are about a spread of 35. So there's more variability in the males' weights than female weights. And you see that because these histograms spreads out a little bit more, and also the range is larger for the males. But since I said this histogram is skewed, and you see that because the median is higher than the mean, the diamond in the box is the mean, the mark in the box, the little line is the median. So the mean is actually being pulled up, and the mean generally follows the skew. So we have all those things in line to use median and IQR to properly describe this. Shape, center, spread, comment on all of those. Comment on each one, have something about shape, have something about center, have something about spread. It would be great even if you made categories shape, dash, talk about it, similarities, dissimilarities. Neatness is always a good thing. If you notice, this all was 6 points, that's why I'm kind of going over it a whole bunch. I don't want you to lose points because you make a little mistake, and you do not want to write one sentence here. You really want to talk about the differences between these groups. Make sure you analyze the shape, the center, and the spread very carefully. Produce side-by-side box plots as described by the jump tutorial. Well, let's go in here and produce some side-by-side box plots. It doesn't matter that I have one selected, but once again, if you have something collected, you can go to rows, Clear row states, having something selected won't be bad. We would not want excluded or hidden though. Once selected means it's just selected like that. So go over here to Graph and go to Graph Builder. We're going to do it a different way today. Let's go here to fit y by x. I am going to put in my variables that I'm using, and let's put in sex, and let's go put in weight right here. So these are the variables that I'm using, not the ones that you're using. So now we have our output, and to get side-by-side box plots, I'm simply going to go here and do quantiles. Side-by-side box plots, magically. We can go up to here and take a new picture of this. We don't really need the quantiles down there, we just want the box plots. And box plots go with quantiles, because when you think about the quantiles, they make up the box plots. The IQR is the middle 50%, and the line in the box is the median. So that's why we have all this. This line in the center of the data is the grand mean. It's for, if we were to average out all the values, we would see that. So you don't exactly need it, and I don't know if there's a way to remove it, but it doesn't really matter. And once again, if you have points selected in here, probably try to deselect them by clicking somewhere, or go to rows, clear row states, and you don't have points selected. Always makes it look nice and neat. Side-by-side box plots, got that. Produce all relevant jump output that allows you to conduct a two-sided hypothesis test. To make the two-sided hypothesis test, we'll do the same thing we did before. So if you already have this open, let's close out the quantiles, and you could just go to t-test right here. But let me show you how to get here if you didn't get here before. Go to Analyze, Fit Y by X, put in what you want to use as your explanatory variable, and put in what you want to use as your response. So we have the data now. We need to go to the red arrow where the options are always at in jump and go to t-test. So now we have our output for the test. With this in mind right here, let's take a picture of it. And this is what we will be analyzing. Now this all is very important for the test. I'll go over a little bit more in depth because I really want you to understand some things here about this output, because with the test coming up, this project can prepare you for the test if you realize the similarities between the project and the test. So let's go back to the question right here. Write out the null and alternative. Well, what are we testing here? We have two groups, and we're testing quantitative data. So we're looking at the means between the two groups. So going into Word, we can do some nice and fancy stuff here. I'm going to increase my font really big. Your font won't be really big. I'm just making it easier to see on YouTube. I'm going to write HO for the null. And if you notice, I got subscript here. The subscript button is right here. I'm using a quick command to get to it. So you can put in the subscript HO, and then you go out of it. I have now deselected it. And you can put that. This is subscript and superscript if you ever want to put those things in for exponents or for subscript down here. So we have the null states. And now we need to say what the null states. Go to Insert, and go to Symbol. We need the mean, the true mean. The null states that the true mean, and I did subscript again, you'll see it's selected over here. The null states that the true mean for males, go out of subscript, is equal to, and let's just copy this, and we'll have to decrease the font maybe, the true mean for, oh, it's not liking me today, the true mean for females. So the null states that the true mean for males is equal to the true mean for females. And it looks like I had this subscripted right here, so let's fix that. There we go. The null states that the true mean for males is equal to the true mean for females. It's kind of weird to think of that, but with this test, we don't assume anything. We're testing to see maybe if males have a different weight than females. And I think that's what this is setting you up for too. It wants you to test out weigh more on average. So it says, do students who smoke marijuana weigh more on average than students who have not smoked marijuana? So in my question right here, I would want to do a one-sided test also, and I would have a one-sided alternative stating, the alternative, I just changed it around there, now the alternative states that the true mean for males, and let's change this, is greater than the true mean for females. So we have this written out right here. We're saying our alternative would be, let's see if there's evidence to say that males weigh more than females. Anytime you say more, less, or not equal to, you're talking about an alternative, because the null states no knowledge of, well, males weigh more than females. The alternative says, well, I will show you evidence that males weigh more than females. Going back here to our output, let's look at the next question. Report the difference. So in my example right here, the difference between males and females, between their means, is 37.81. It might even say that when I hover over it, because it was saying something before. Difference of the means. That's what it says right there, of course. With this in mind, when you see male minus female, it's saying right here, if we were to take the mean for males, which was like 100, and do we still have that in the SNP? No, we don't. The mean for males was 37.8 higher than the mean for females. If you go back and look at the previous part of the video, you will observe that. This is the true observed difference between these two means up here. Actually, I can get some output with the means. The difference in the means is denoted right here, and it's 37.8 or so. There's the mean for females, and there's the mean for males right there. And we see that 37.8 difference about. So let's remove that extra output, and there it is. There's the difference, and we just looked at the means for both of them, and it's true, as we would expect. So we report the true difference between the sample means. If you notice, this is the true difference between the sample means. What does this mean? This means that we observed in our sample of 90 students that males weighed more on average by 37.8 pounds than the average weight of females. The difference in the sample means of males and females that we observed is 37.8. That is what we are saying. Multiple ways to write it down. Just make sure you write it clear and concise. Report the appropriate value for the p-test. For the t-test. I was like, where is it? I saw p-value and it's immediately read p-test. Report the appropriate value for the t-test, and this is a t-test. So going back here to the output, we're going to look at this t-test. This is a two-sample t-test because we have two groups right here, males and females. And when we look at this right here, we need to take this value right here, this greater than or less than, and put it into that dash right there. Males' weight, or the true mean of males, is greater than the true mean of females, would be the p-value right here. Now, when we have a small p-value, that means evidence for the alternative. The null would be that an equal sign goes right here. If you want to think about the null, it's that the true mean for males equals the true mean for females. And that's the null. When the p-value is low, we reject the null. So with this in mind right here, does this look like a small p-value? Oh yeah. And this is the one for the alternative, males greater than females. Just put the greater than right here, males greater than females. And I want you to think about this graph over here on this side. What did we expect the difference to be? What did we expect the difference to be? As I'm hovering over it right here, 0. Because if males equal females, the null states the difference would be 0. That's what we're doing with this test. And then we're seeing, well, what was the difference, and would that happen by chance? Well, if males weighed 2 pounds more than females on average, that would be kind of, that could happen if the true difference is 0. But we landed all the way up here at 37.8. That wouldn't happen by chance. This is all random variation. Remember, the p-value is the probability that our results, or results more extreme, would occur due to random chance variation given the null is true. A layman's way of thinking about the p-value, which is not perfect interpretation, a layman's way of thinking about it is the p-value is the probability the null is true. And if you look at this, if we're saying that our alternative is males weigh more than females on average, or the true mean of males is greater than the true mean of females, is this p-value enough evidence for the alternative? Well, there's basically a 0.00001% chance that the null is true, and that doesn't seem like the null is true. It seems like we have evidence males weigh more than females. We have shown evidence. This is far enough away from the null. The further you are away from the null, the more likely it is that there's an alternative over here that males weigh more. Let's go back and look at the test questions, or the questions here. State whether you reject or fail to reject. Oh, with this p-value, this p-value is 110% reject. 110% doesn't even make sense, but that's reject. Anything below 0.05 is reject. Your p-value, I want to state this, your p-value might not be the one I'm hovering over right now. I'm doing the test to see if males weigh more than females. Make sure you select the appropriate p-value to see if it's, I think the question was, let's look at it. I think it's, do students who have smoked marijuana weigh more on average than students who have not smoked marijuana? So you need to see if yes is greater than no. That's what you need to test, is yes greater than no. Do students who have smoked marijuana weigh more on average than students who have not smoked? So with that in mind, let's go back right here to our jump output. We'll keep this open inside. Next question. Do we reject the null? Yes, definitely, because our p-value is below 0.05. Carefully state your conclusion. Is there a statistically significant difference between the weights? Definitely. With a p-value below 0.00001, I have statistically significant evidence to state that males, the true mean for males is greater than the true mean for females. I have very strong statistical evidence for that. Right here, the true difference between these two groups is not equal to 0. Thus, the null is false. Thus, we should reject it. However, your relatively small sample size for your test may have lacked the power to detect the truth. What is the name of the type of error when the null is not rejected but it is false? So if you're my class especially, the null is not rejected but it's false. That is a false negative. It's like going to the doctor and they say, oh, you do not have the bubonic plague, but you do. Your test results come back negative, but they should have been rejected. This is a false negative. We did not reject the null. With this in mind, if we fix alpha, what is the only way we can decrease the frequency of this type of error in general? There are three things that control power of a test. There is alpha, and when alpha goes up, the power of the test goes up. There is, I was about to say the next one, there is also effect size. Effect size is the difference between the truth and the null. And here there's a huge effect size. But you can't really control that because you can't control, like, from our samples what the difference would be. Now there's one last thing, and you might have to go to your notes. It kind of tells you in this problem, though. There's one last thing we can change, or we could go back and change and redo with this thing. But there's something that researchers can change to make their test more powerful. And as that increases, so does the power of the test. So think this over a little bit, go back to your notes and look at what controls power. To go on a little bit more about this problem, when you get to this chapter, you will notice that anytime we do a test, all we're doing is putting a difference in terms of some sort of standard deviation or standard error. This is just like a z or t-score. It is a t-score. But it's just like a z because when you think about it, we're saying that this is almost 6.56 standard errors of the mean above 0. That's really far away. If you think about your 68, 95, 99.7 rule, we're just finding out how big the difference is here in terms of standard errors of the difference. And it's the same concept as the normal curve with 3 standard deviations is really far away. And we landed really far away, so this doesn't look to be true. It doesn't look like this would happen naturally given this over here. Once again, to get this 6.56, all you have to do is just divide these two numbers. 37.8 divided by 5.7. Also down here, we have a confidence interval for the true difference. The confidence interval for the true difference does not contain 0. We're saying we're 95% confident that the true mean difference between males and females' weights is contained in the interval 26.35 pounds to 49.27 pounds, with males weighing more than females, on average. So that means that 0 is not in here. Once again, if 0 is not in the interval, we would reject for a two-tailed test with a corresponding alpha level. There's a 95% confidence interval, so we would, of course, right there it states it, we'd reject at the 0.05 level, but it's 0 is way out of this interval, and this test is extremely significant. All these tests, the top two. The top one states the alternative, there is a difference, and the p-value would look something like we would need another line down here, and it would be shaded here, and it would be shaded here. It would just be double. And then the p-value here for this one would say the alternative, females, the true mean for females is more than the true mean for males, because we're stating the true mean for males is less than the true mean for females, so of course we flip that. the true mean for females is more than the true mean for males, and that would be shading from here down, which, yeah, that's a humongous p-value. We do not have evidence that on average females weigh more than males. That doesn't hold true. So once again, know how to do that stuff for the test. The project is meant to prepare you for the test. Down here it says that 5 points are given for neatness. I'm going to make a short neatness video with just a few suggestions of my own. But yes, good luck.